Today we're going to look at rational functions. And a rational function is of the form f of x over g of x, where f and g are both polynomial functions and g of x cannot be 0. A reciprocal function is a special case or a special type of rational function in which we have 1 over g of x. So a rational function, the rational functions we're talking about today are a little bit more general in nature. It's going to be some kind of variable polynomial function over another variable polynomial function. Some of these graphs can get kind of complicated to graph, so there will be certain things that we would expect you to know how to do and get without the graphing calculator, and for other things we will ask you to actually use the graphing calculator. So with the calculator, without the calculator, we would expect you to be able to find the domain of the function, and that's typically where you would look at the restricted values of the function where the denominator is equal to 0. At those undefined points, what will happen is one of two things. You'll either have vertical asymptotes at those points, or you'll have a hole in the graph. And I'll show you an example of each of those in a moment. The x-intercepts of the graph, the zeros of the function, occur when the y value of the function is equal to 0. So if you look back at our rational function form, when y is equal to 0, you only get 0 out of a fraction when the numerator is 0. 0 over a number that's not 0. 0 over a number that's not 0 would be 0. So the x-intercepts occurring when y is 0 occur when the numerator is equal to 0. And the y-intercept of any function we know is when the x value is equal to 0. Things that we would expect, or that you would need to use your graphing calculator to determine. Range is always more difficult than domain, so you would get your range from the calculator in most cases. The horizontal asymptotes, same thing with that. You would use the trace feature on your calculator to approximate where you think those would be. Again, I'll show you an example of that. And then symmetry, either about a vertical line. The y-axis is what we would be asking you to look for. Line symmetry or rotational symmetry of 180 degrees about the origin. So this rational function consists of two lines divided together. Let's actually look and see what this function looks like on the graphing calculator. When you enter a rational function in the calculator, you need to ensure that you bracket the numerator and the denominator as shown here. And then if we bring up our graph, we see a number of features on the graph. For example, we see a vertical asymptote right here at x equals 1. Graphing calculators sometimes have trouble showing asymptotes. Remember, an asymptote isn't actually part of the graph. It's just sort of an invisible line that the graph approaches. The calculator is showing the line due to a situation with its pixel structure. So you got to remember when you see a line just flying down like that, that's not part of the graph. It's the graph approaching that line on both sides. When we draw our graph on the grid, we'll do that as a dotted line. There also seems to be a horizontal line going across somewhere around here in which the graph is approaching on both sides of this line. If I actually take my trace feature and I trace along the graph, and if I do this far enough, I'm basically going to try to see what value of y does the graph seem to be approaching. And if I keep doing this long enough, and I'm going to have to go out fairly far, in fact, quite far. Let's just change this to 100 to show you how far. If we actually keep tracing, we're going to find that with time, the y value is going to get closer and closer to 2. And you can do that on the other side and see that the same type of thing is happening. All right, so let's go back to our main board here and just sort of put some of this stuff together. So first of all, our domain we determine by the values of x where the function is undefined. That's at x equals 1, so x can't be 1, but it can be any other value of x. Associated with that, at a point where it's undefined, we're either going to have a hole or a vertical asymptote. Well, we saw from our calculator that we had a vertical asymptote at x equals 1. We'll see an example of a hole in the next example, so this is not applicable in this case. The zeros of the function, the x-intercepts are when y is 0. When y is 0, that means that the numerator must be 0. So that's 2x plus 5 is 0. And if we solve that through, minus 5 divided by 2, we're going to get negative 2.5. All right, so we've got an x-intercept of negative 2.5. There's a vertical asymptote here at x equals 1. For our y-intercept, we're going to make x 0. So when x is 0, plugging that in, that would be 5 over negative 1, negative 5. So our graph's going to cross down here. And the remaining items we need to look at our calculator to decide. So going back to our sketch, for the range and for the horizontal asymptote, when we did our tracing, we noticed that the graph seemed to be approaching this line, y equals 2, that I'm dotting in. That's the equation of the horizontal asymptote. And then for the rest of the graph, I'm going to rely on what I see on my calculator. I'm going to make sure that my graph hits the zeros, the y-intercept, approaches the asymptotes, and that will be deemed sufficient detail for this graph. You know, up in this section, I might want to have a point of accuracy. So I might want to know, for example, when x is 3, what's y? I could plug x equals 3 in here to figure out what that is. Or I could use my calculator and type in when x is 3, y is 5.5, just to give me a little bit of accuracy. And then following the pattern of what I saw, I know my graph is going to go up and look like something like this. Okay, so my range is going to be all values of y, except y equals 2. So y can't be 2, but it can be anything else. And in terms of symmetry, I don't see any symmetry. The graph doesn't look like it's symmetric about the y-axis. If I flip, I'm going to get something different. If I rotate 180 degrees, I'm not going to get a match. So there doesn't appear to be any symmetry. No symmetry. Let's look at our next example. Before we enter this into the calculator, let's just spend some time doing what we can to analyze it. So the domain of the function, well, x can't be 2. Now, as we know, where the function is undefined, that means we're either going to get a hole in the graph or a vertical asymptote. How can we decide? Well, you would probably notice in this question that the top could be factored by a difference of squares. And then once I do that, my problem that was creating the fact that I couldn't put 2 in is now going to be resolved because that's going to cancel out. So my function is going to reduce to y equals x plus 2. Okay, so you say y equals x plus 2. That's a line. That's the graph of a line. It is. Okay, but we got to remember that that's with the condition that x can't be 2. So if I graph y equals x plus 2, the equation of a line with a y-intercept of 2 and a slope of 1, I'm going up 1 over 1, up 1 over 1. Now when I get to this point right here, that's the point I can't use, right? Because we were told originally that x couldn't be 2. If x could be 2, y would have been 4. Okay? And since we know all the other points around it in the shape of a line or in the pattern of a line, what we're basically doing is missing one point right here in the middle. Okay? So this is an example of a point where the graph is not defined, in which at that point we have a hole in the graph. And what are the coordinates of this hole in the graph? 2, 4. There are no vertical asymptotes in this situation. So what you'll notice is that in distinguishing between whether you have a hole in the graph, as in this example, or a vertical asymptote as in the last example, what it's going to come down to is whether or not your rational function is reducible to a polynomial function. If it's reducible to a polynomial function, then when the function is undefined, there's going to be a hole at that point on the graph. In the last example, the function was not reducible to a polynomial function. Therefore, where the function was undefined at 1, we ended up with a vertical asymptote at that point. All right, so we were able to graph this without a calculator at all. If I actually did type this function into the calculator, we'll just turn this function off and turn this next one on and bring it up. I indeed get a line, the y-intercept of 2. You don't see the hole very clearly on the graph unless you were to change the window dimensions a little bit. So you need to remember that when you're graphing this on paper, you would be expected to show the place where there's a missing point on the graph. Just finishing off with a few more things that we would expect you to find on a graph such as this. Without a graphing calculator, we would expect you to find the zeros of the function, which is where the numerator is 0. All right, well, since the x minus 2 canceled out, we're left with x plus 2 being 0, which means x is negative 2, which by using my slope, I can see that it actually would, in fact, intersect there. The y-intercept, when x is 0, would be 2. Okay. The range of the function would be all values of y except that one right there, except y can't be 4. And there are no horizontal asymptotes, and in this case there is no symmetry. Let's look at one final rational function, x over x minus 1. Let's do as much as we can without looking at the graphing calculator. First of all, domain, where is the function undefined? When the denominator is 0. X cannot be 1. At the point where it's undefined, there will either be a hole or a vertical asymptote. It's a hole if this is reducible to a polynomial function, and it's a vertical asymptote if it's not reducible. Well, there's no way to cancel the x and the x minus 1, so we're stuck with the x minus 1 on the bottom, which tells us there will be a vertical asymptote at x equals 1. No holes in this situation. So let's dot in our vertical asymptote at x equals 1. The zeros of the function are when y is equal to 0. That would be when the numerator is 0. So at x equals 0, we have an x-intercept. The y-intercept is when x is 0. When x is 0, y is 0. It's the same point as the 0. And remember, those are the only things we can determine at this point, given our mathematical knowledge about this function, without now looking at the graphing calculator for the rest. So off we go to the graphing calculator, and we're going to bring up this function. Here it comes. Okay, we have our asymptote as expected. We have it crossing at x equals 0 as expected. We seem to have an asymptote occurring here. Let's trace the graph to see. Let me trace towards the left this time. You should really trace in both directions to ensure that it's approaching the same value. As I keep going, it seems like we're on our way to y equals 1. Okay, you can expect on the graphs we gave you that the horizontal asymptotes, if there appears to be one, will be approaching likely some nice convenient number. Okay, so in this example, y is equal to 1. Dot in our asymptote. And to finish off, follow the sketch from the calculator and putting it all together. Our graph's going to come down something like this. If you wanted to take some time and get a point, accuracy point for better accuracy, that would be great. Down here, let's make sure we hit our 0 and then our asymptotes as we saw on the calculator. Okay. The range, all values of y except 1. So y can't be 1, but it can be anything else. There doesn't seem to be line symmetry, and there doesn't seem to be point symmetry about the origin. There might be point symmetry around here, but all we would ask you to look for is the point symmetry around the origin, which doesn't exist. None. Best wishes with rational functions.